In our first chapter on probability, we looked at an example like this one here where we had a pair of dice, a red one and a green one, to make sure they're very distinct here. And we had 36 possible outcomes if we rolled them 6 times 6. And we could look at the sum on the dice, and that's what we're going to do here with a conditional probability. A red die and a green die are rolled. What is the probability that the sum on the dice is 8, given that the sum is greater than 5? So if we know it's greater than 5, it's a 6, 7, 8, 9, 10, 11, or 12 would be the highest possibility there. So we've shrunk the sample space. So I've got a picture here on the next page. And I've put the sums beside them here. So if we rolled a 1 and a 1, the sum would be 2, and so forth. So there's our 36 possible sums listed beside the pictures. And so we were looking for the probability that we rolled in a sum of 8, given that the sum is greater than 5. Was it greater than 5 or less than 5? Greater than 5. So I've drawn this kind of staircase here. We can eliminate all of the possibilities where the sum is less than or equal to 5, and now our sample space is the lower part of the table here. And we're looking for the probability we get an 8, which would be 1, 2, 3, 4, 5 out of however many there are there. Okay, so there's 5 possible rolls of the dice where you get a sum of 8. Out of, if you count them up, there's 26. It's probably quicker to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them that we're throwing out of the 36, so there's 26 left. So of the 26 left, if we know that the sum, so here's the conditional part, and there's the symbolic way I can write it. The probability that the sum is equal to 8, given that the sum is greater than 5, would be 5. There's 1, 2, 3, 4, 5 ways to roll an 8 out of 26. There's not 36 possible outcomes. If we're given that the sum is greater than 5, there's only 26 possible outcomes. Okay, next, before we get to the full-blown formula, the multiplication formula for probability of A and B, we're going to define independent events. So independent, kind of conceptually or in words, two events are independent if they don't influence each other, in the sense that knowing that one occurs doesn't tell me anything about whether or not the other occurs. Symbolically, we can define that in terms of the conditional probabilities. If the probability of A given B is equal to the probability of A, that's telling me that knowing that B occurred didn't change the probability of A at all, then the events are independent. That's the definition of independent. And equivalently, if the probability of B given A is equal to the probability of B, they're independent. Okay? So the conditional probabilities don't change because knowing the extra information about A or B doesn't tell me anything about the other when they're independent. That's the definition of independence. And if we go back and we look at the formula for the probability of A given B or B given A, we can multiply and get a formula for the intersection, which simplifies when they're independent. But you wind up, if you take the formula that was on the previous slide, when we did the one for conditional, we had that the probability of B given A was equal to the probability of A and B divided by the probability of A. Well, if I multiply, I get this formula, the probability of A and B, which I can write with the intersection symbol, the one that looks like the union symbol looks like a U. It's the other way around. This one looks kind of like an N for intersection. So the probability of A and B, which is what both of these say, one symbolic, one in words, would be equal to the probability of A times the probability of B given A. So when you do an AND, you multiply, and if they're not independent, you have to use conditional probabilities as you go along. If they're independent, then the probability of A given B or B given A is just the regular probability, and you just multiply. The probability of A and B is the probability of A times the probability of B when they're independent. Okay? So a lot going on there, but if you look back, we have our formula. The probability of B given A is equal to the probability of A and B divided by probability of A, where I said you're just shrinking the sample space. A success would occur when they both occur if you're given that one of them already occurs, and you've shrunk the sample space down to just A in that case. If we multiply, we get this formula. The probability of A and B is equal to the probability of A times the conditional probability for B. Or you can reverse the letters, really literally just reverse the letters A and B, and you'll get that the probability of A and B could also be written as probability of B times the conditional probability A given B. So what you do is you multiply the two together, and the second one has to be the conditional probability, unless they're independent, in which case the conditional probability is just the probability of A or B, depending on which one you're looking at. I think it makes a whole lot more sense when you see it in action here. Okay, so here's an example with a deck of cards. Suppose that from a deck of 52 cards, so a standard deck of playing cards, 2 cards are drawn in succession without replacement. So I draw one out, put it to the side, and then draw another one. And let's assume that it's well shuffled, completely random here. Okay, find the probability that both cards are kings. So I have in words here the probability that the first card, if they're both kings, then the first one's a king and the second one's a king. So that's what we need, the probability that the first is a king and the second is a king. Well, by our rule, that'd be the probability the first one is a king times the probability that the second one is a king, given that the first card was a king. Okay? So there it is written out in words and the probability symbols. And we can think about the numbers there, okay? The probability that the first card is a king, so just think about the deck. We've got a deck of cards and we're going to draw a card. There's 4 kings out of 52 cards, so the probability that the first card is a king is 4 out of 52. We take that card and we put it to the side and we're going to draw another one. There's only 51 cards left, and there's only 3 kings because we took one away. This is the conditional probability. If we've already drawn a king, the probability that the second card is a king is going to be 3 out of 51 because there's 3 kings, 51 cards. So we're multiplying the 2 probabilities together for the first card that we draw and then the one for the second card that we draw. The second one technically is a conditional probability, but I just think about what's going on. We've got 52 cards for the first one. We've only got 51 cards for the second one. And if we already drew a king, there's only 3 kings left. So you multiply them together, you get fractions with some large numbers here, 12 out of 2652, which if you divide out as a very small decimal, it's a very small probability, less than 1%, that if you draw 2 cards at random, you get 2 kings. You get 0.0045. Another example, we've got these colored balls in a box. You got colored balls, colored chips or something in a box. So we can count things up. In this case, I've said they're balls. So we have a box containing 4 black balls, 3 red balls, and 5 white balls. 1 ball is drawn. This is very similar to the card problem we just did. 1 ball is drawn and it's not replaced, and a second ball is drawn. Find the probability that the first ball is black and the second ball is white. So again, I'm going to start with the words here. We want the probability that the first is black and the second is white. So we would multiply the probability that the first is black times the probability that the second is white, given that the first was black, since we're not putting the ball back in. Okay? Probability that the first one's black would be 4 out of, if we add them up, we've got 12, right? 4 plus 3 would be 7, plus 5 would be 12. So 4 out of 12 would be the probability the first one's black. So think about that. We've taken one of the black balls out of the box, and we're going to draw another one. What's the probability we get a white? Well, there's only 11 balls left, but there's still all 5 of the white balls, so 5 out of 11. So that would be our probability, 4 out of 12 times 5 out of 11, which comes out to be 20 out of 132, or 0.1515, so about 15%.